Hello, everyone. Welcome back. So right now, we're going to talk about polynomials. We'll learn what they are, basically understand the concepts of a polynomial, what they are, kind of some things about them. Be able to find the zeros of polynomial, also what's called the multiplicity of the zeros. We'll explain that. And also be able to explain the long distance behavior of a polynomial when you're far from zero. So first, let's look over on the left. So the definition of a polynomial, and this is kind of the official like mathematical definition of it. And it may look complicated, we'll break it down. And because most of the time we'll be looking at ones that are simpler than this, of course, but this is kind of a general definition. So it's a function where in this case it's a function of x. All right. Now, the nice thing about polynomials, what makes them polynomials opposed to other kinds of functions, is that our powers are all whole numbers. Remember, whole numbers are 0, 1, 2, 3, and so forth. So no negative powers, no powers of fractions, or powers of decimals, anything like that. The exponents are all whole numbers. And the coefficients, the a's, numbers in front of the x's, are real numbers. Okay, now they can be kind of any kind of real number, fractions, decimals, positive, negative, whatever. Now, polynomial is usually written in what's called descending order. So usually the highest power of x first, then the next highest power of x, and all the way down to the lowest power of x, maybe just x to the first power, if there is one, and then the constant, okay, if there's a constant. And we call whatever the highest power is, we call that the degree of the polynomial. Okay, but many of these terms, all these terms don't have to be here, all the way down to every power from the highest power of the constant don't have to be there. Sometimes they will be, but sometimes they're not. Now, it says usually written or best written is what's called descending order, once again, from the highest power, the next highest power, and so forth. And the leading term, the term with the highest power, is called it's called the leading term. That's what gives you what's called the degree of the polynomial, which is your n. Okay. And a polynomial of n degree, whatever the n is, has n zeros, and these are zeros of a function, real or or imaginaries, and some can also be repeated. So we'll talk about these concepts as we look at some examples. So let's do that on the right. Let's just look at some examples of polynomials. Okay. So technically, just a constant is actually a polynomial. Constant like that. Okay. And this would have a degree of 0. Okay. Because there's no power of x. Now, a linear function, f of x is equal to negative 3x plus 2. Okay. That's also a polynomial. Because in this case, let me back up a minute. The constant, it's a polynomial because think of this as being like x times x to the 0 power. Of course, anything to the 0 power is 1. A linear function like this is also a polynomial, okay? Because our x, the variables to the first power. And here, our degree is going to be just 1. Okay? And we have a quadratic function, so like maybe x squared plus 2x minus 9, for example. And its degree, of course, is 2. Now, also in terms of zeros, functions don't necessarily have to have zeros, or at least real zeros. But, like, for example, a linear function like this will have 1 0. In this case, have a real 0. A quadratic function will have 2 zeros, and they could be both real, could be both imaginary, and also could be repeated in some cases. So we'll see examples of those. Okay, and so on. So we can do like a cubed function, 2x cubed, say plus x. Yeah, just have 2x cubed plus x. In this case, they all once again have this form in descending order, highest powered first. Okay, this one has a degree, of course, of 3. Okay, and talk about leading terms. The leading term of this one is the highest power of x, negative 3x. Of this one, the degree is 2. This one has a degree of 1, since the highest power of x is 1. This one has a degree of 2, since the highest power of x is 2. Its leading term is this, x squared. This one, once again, has a degree of 3, since the highest power of x is 3, and its leading term, this leading term is 2x cubed. Okay, and so forth. You can go as many, so you can have as high a power as you want of x, as long as they're all whole numbers. Okay, nice numbers. Let me do one more. So let me just do one. We do like I don't know, we'll see with decimals, so 0.109 x to the 7th minus 1.312 x squared minus 4.100x. Okay, that would be a degree of 7 polynomial. Okay, and this is the leading term. And as we'll see, the leading term is important because actually our behavior far from 0 is essentially determined by our leading term. So these are all polynomials. And like I said, they're nice functions because they're easy to work with because the exponents are just whole numbers. Okay, now let's briefly talk about some examples of things that are not polynomials. These are just some examples. Okay, so these are still functions, just not polynomials. For example, 1 over x. Okay, because that's the same thing as x to the negative first. That would be a negative exponent, so that's not a polynomial. Still a function, but not a polynomial. Okay, or f of x is equal to, like, say, the square root of x plus 2. Here, once again, not a polynomial because our power would be the same as a radical. This would be the same as the 1/2 power. Okay, or if we had like f of x equals x to the 2/3 power, also not a polynomial since our whole number is not, our exponent is not a whole number. Okay, or even, let's see, creative, x to the square root of 3. Once again, not a polynomial since our exponent is not a whole number. Okay, and let's just do one more quick one. How about f of x is equal to 3 plus I times x squared? Okay, what's wrong with this one? Well, in this case, this is a little more unusual. Our coefficient is not a real number. In this case, that's not a polynomial either. All right, so hope you see partly the difference is polynomial functions are nice functions. They're easy to work with. Okay, so those are the ideas of polynomials. So now let's talk about the zeros of polynomials. So remember, a zero is a solution of any function. A zero is the solution of the function f of x equals 0. So if we have our general expression for a polynomial function, if we set that equal to 0 and solve it, then that will give us, if we can solve it, that will give us the zeros of that polynomial function. Okay. Now, if it can be factored, and that's not true in every case, but can be factored, then basically you can find the zeros by factoring the polynomial and just solving that function equal to 0. Okay. And then also, if a polynomial has real zeros instead of complex zeros, basically that 0 is going to be the x-coordinate of an x-intercept. So basically, you can estimate the real zeros by the graph of the polynomial. Okay, so let's take a look at a few examples. So let's say we want to find the zeros of the polynomial. Okay, so number one, let's say we have this for an example. Let's say we have f of x is equal to x squared plus 2x minus 3. Okay, now, once again, this is a polynomial function. All our powers of x are whole numbers. It's in descending order, highest power of x, and the next highest power of x, and so forth. This is a second degree polynomial since the highest power is 2. Our leading term is x squared. Okay. Also, we'd expect this to have 2 zeros where they, could be both real, could be both imaginary, or also could be one, could be repeated. Okay. Now, so to find the zeros, want to solve f of x equals 0. So we do that, and we have x squared plus 2x minus 3 is equal to 0. Now, realize this is now a quadratic equation, which can be solved with a quadratic formula, but this one also will factor. And this factors into x plus 3 and x minus 1. Okay. Now, if you can't factor it or have trouble factoring, you can always use the quadratic formula. Now, from here, once it's in factored form, we can solve this by setting each non-constant factor equal to 0. So if x plus 3 is 0, x minus 1 is 0, then if you solve each one of those, so our solutions then are x equals -3 and x equals 1. Okay, so these are our zeros of our function, because those are the number, if you plug these into your function, will give you 0 on this side. And these are also, this also tells you, since these are real numbers, you also have your x-intercepts. You have coordinates -3, 0, and 1, 0. Okay, so let's actually look at this one quickly on Desmos. Our site we go to is desmos.com, and let's type this in and see. So y is equal to x squared plus 2x minus 3. Okay, we look, there are zeros. Okay, so once again, the zeros are the x coordinates of the x-intercepts, and so our zeros are your -3 and 1. All right, now imagine, now let's change something in this. Let's make this set of -3, make this +3. Notice what that does. In this case, if you had this function, then you would have, you no longer have any real zeros. This doesn't cross the x-axis. In that case, you'd have 2 imaginary zeros. We still do have zeros. Right now, we're focusing on real zeros. In that case, you'd have imaginary zeros. So there's no x-intercept of polynomial, then you have imaginary zeros. Okay, and you can have a combination of both real and imaginary as well. Let's go back. Okay, now let's introduce the next idea, which is something called multiplicity of real zeros. So the multiplicity of a real zero is the number of times the real zero occurs in the factored form of the polynomial. It's the exponent of the factor when where the zero comes from. So what I mean by that is, basically, it's a question of if any of our zeros are repeated, and sometimes they will be. Okay, so let's take a look. For example, this one. Okay, so look at each zero and look at each factor where it comes from. This zero here, -3, comes from x plus 3, and that factor has a power of 1, only occurs once. This x equals 1 comes from our factor x minus 1, and it is only has the power of 1. Okay, so each zero has a multiplicity of 1. Okay, now let's take a look at another example. And I understand this kind of explains this idea of multiplicity a little more. Let's take a look at a really familiar example of a polynomial function. How about simply f of x equals x cubed? Okay, cube function. Now, in this case, we don't have to factor it. Okay, we want to find the zero. So we basically want to solve f of x is equal to 0. Okay, and we do that, we get x cubed equals 0. We know what real number makes that true is just x equals 0. Okay, so in this case, we have one real zero. Actually, it turns out that actually it has other. Well, this actually is. I'm sorry. Let me take it back. This has a one real zero. Okay. Okay, but it has a multiplicity of 3. Okay, since it occurs 3 times, it has a multiplicity of 3. Okay, meaning that basically it's kind of repeated 3 times in a sense. Okay, so that's how the multiplicities. Let's take a look at another one. Let's take a look at some functions already in factored form. So we have f of x is equal to x times x plus 2 squared times x minus 4 cubed. Okay, now let's say this is our function, and it's already in factored form, so we don't have to worry about factoring it. Now, to find our zeros, once again, we want to solve f of x equals 0. Okay, so we just take this and set equal to 0. So x times x plus 2 squared times x minus 4 squared equals 0, or cubed equals 0. Okay, now, so set h now. So the factor we can do now, since it's in factored form, if any of these three factors is 0, it makes the whole thing 0. So we want to find out what it makes each one 0. That will be a solution. And so we set x equal to 0, x plus 2 squared equals 0, and x minus 4 cubed equals 0. Okay. Now here, I think it's clear to see what makes each one 0. This is already solved. 0 will make this one 0. You know, so plug in 0 for x everywhere. Because this one is 0, it makes the whole side 0 and makes this a true statement. Now here, what number will make this 0? If x is negative 2, that will make this true, right? And over here, if x is positive 4, plug in b4 minus 4 is 0. Okay, so those are our zeros. Okay, now if we look at the multiplicities, okay, so x equals 0, so it has a multiplicity of 1, this only occurs once. X plus 2, or I'm sorry, just 0, okay, just the 0 itself. Okay, so x equals negative 2 has a multiplicity of 2, since that was the power of the factor it came from. Okay, it has multiplicity of 2. And then, as you can probably guess, x equals 4 has a multiplicity of 3. Since the factor it came from was through the third power. And that's the idea of multiplicity. And what you see then, and if you graph something like this, what you're going to see, in fact, let's graph this one, is that basically, so what would this be in terms of powers? So we'd have 3, essentially, if you multiply this all out, you'd have 3 powers of x here, another 2, and 1. This would actually be a 6-degree polynomial, okay, if you multiplied it out, all right? This is a 6-degree polynomial. So your highest power of x would be 6, since we have 1x here plus 2 plus 3 is 6. Now, what that means, we expect to have then, in this case, we have 6, or at least a 6-degree, it's a 6-degree polynomial, okay? But you're not going to find, there are not going to be 6 distinct intercepts because these two are multiplicities, okay? So let's actually graph this with Desmos and see. Okay, so here we have y equals x times x plus 2 squared, okay, then times x minus 3, x minus 4, rather, cubed. Okay, you see it's kind of a strange looking one, right? But what we're interested in is where it crosses the x-axis. So we said one of our intercepts have at least one intercept there, -2. But you notice from here, it only happens once. Okay, even though it's a multiplicity of 2, even though 2 factors with x plus 2, it only occurs once. Also here with 4, okay, that even though it's a multiplicity of 3, it only crosses there at 4 once. Then also we have 1 at 0. So we have 3 distinct zeros, okay, and in this case 3 real x-intercepts, but different multiplicities. We can also mention that. So our x-intercepts of this function are the origin 0, 0, -2, 0, and 4, 0. Okay. All right, let's look at one more. Now, number 4. Okay. Let's say this time we have f of x is equal to -3 times x plus 1 to the 5th times x minus 7 squared. Okay. Now, let's say this is our polynomial. Now, what degree would this be? Well, if you multiply this all out, we can think about our powers of x. Remember, thinking like, so you'd have 5 powers of x here and another 2. So this would be a 7th degree polynomial. Okay. But we don't have 7 distinct roots. So once again, we just find our zeros. So we solve f of x is equal to 0. We have -3 times x plus 1 squared times x minus 7 x minus plus 1 to the 5th, then times x minus 7 squared is equal to 0. Okay. Now, notice 3 doesn't play a role in our zeros. It's just a constant. So the best thing to do with that is divide both sides by -3 to get rid of it. It's just a constant. Okay. So that leaves us then with x plus 1 to the 5th, and then x minus 7 squared equals 0. Okay. Now it's in factored form, set each factor equal to 0 and solve. And so that's going to give us then x plus 1 to the 5th equals 0, and x minus 7 squared equals 0. In this case, we can see which will make each one 0. This one, if x is -1, that'll make this 0. That'll give us a true statement. So this is a 0. And then this one, if it's x equals +7, plug that in, that would make this one 0. So these are our zeros. Okay. Then our multiplicities. Okay. So x equals -1. It has a multiplicity of 5. So essentially this one occurs 5 times. And this one, x equals 7, has a multiplicity of 2, as we can see. And so if we graph this one, let's go back to Desmos. So, and also we write one more thing, our zeros, or real zeros, or x-intercepts. Okay, one of them is going to be -1, 0, and the other one is going to be 7, 0. And we'll see that. Okay, so we have -3, then times x plus 1 to the 5th times x minus 7 squared. Let's turn this one off. So y is equal to -3 times x plus 1 to the 5th, oops, raised to the 5th, times x minus 7 raised to the 2nd. Okay, and just as we said, okay, -1 and 7. So those are what I call repeated roots, and that's what it means by a multiplicity. Okay. All right. So that's the idea of finding the zeros of a function. Now, in many cases, you can't factor a function. So you may just have to plug it in and graph it. And then you can estimate the real zeros that way. And then that will give you the idea of the real zeros are the x-intercepts. Okay. Now, let's look at our last topic, which is what's called the long-term behavior or long-range behavior of a polynomial. Okay. So what do we mean by this? Well, what we mean is that how a polynomial acts far from 0 is predictable based on the leading term. Okay, let's look at a couple examples. I'm going to make up some. Okay, so number 1, let's say we just do a quadratic one. So f of x equals x squared minus 4x plus 7. Okay, now I'm going to look at my leading term is positive x squared. Okay. Okay. And turns out far from 0 is basically just like x squared. Okay. And all this stuff is important close to 0. It's not as important far from 0. So look at the leading term and what this says over here. Okay. Let's look at our guidelines. So if your leading term is positive, which it is, and the power of the leading term is even, which it is, it's squared, okay? So then what this means is that look like far away from 0 is going to look like this. So basically, when you get far from 0, either positively or negatively, it's going to go to infinity. That's what this says. Goes to infinity of x far from 0, whether you're positive or negative. These squiggly lines here means we don't really know what's going on right here, close to 0. But far from 0, it will look like this. Okay, now let's take a look and prove that. We'll go back to Desmos and actually save these here. So I had y equals x squared minus 4x plus 7. Okay. Now it's just a polynomial, just a parabola. Okay. And we can see right here that basically that's what's happening. So far from 0, it's going straight up, or going up really quickly, far from 0. Okay. Now let's compare that just a graph of y equals x squared. Okay. Now close to 0, they're quite different, but as we zoom out, see they're doing basically the same thing far from 0. Okay. So in both in the positive direction and the negative direction, they're both going to infinity. Okay. Now, let's go back and look at another one. Number 2. Let's do another one with a even root. So let's say negative 2 times x to the 6 minus 5x squared plus x plus 1. Okay. Now, once again, this is my leading term. Okay. Now, what does it say over here? These are our guidelines. So it says the leading term is negative, which it is, and the power of the leading term is even, which it is. It's a 6. Then the polynomial goes to negative infinity when x is far from 0. So basically, this looks like this flipped over. So far from 0 is going to look like this. And once again, we don't know what's happening here, right here, close to 0. But we know that far from 0, it's basically going to go to negative infinity. That's because it's going to act a lot like, far from 0 is going to act a lot like this leading term. Okay. Let's take a look at that. Let's go back to Desmos. We'll graph that. We'll also graph that along with essentially the leading term by itself. So this is y equals negative 2 times x to the 6th. Oops, let me zoom in some. There we go. Minus 5x squared plus x minus 1. Okay. Now, as we can see what happens far from 0, either in a positive direction or negative direction, that's what's happening. It's going toward negative infinity. Now, let's also graph, let's zoom back in here again. Let's also graph just y equals negative 2 times x to the 6th. Okay, that's what it looks like. So you see it's different close to 0. As we zoom out, the base has the same behavior. So what that means is that far from 0, a polynomial basically acts like its leading term. Okay, so that's kind of how we can predict the behavior of these things far from 0, because they look, their behavior is essentially identical to what the leading term is doing. Okay, let's look at another one. Now, this time let's do an f of x. Let's look at one with an odd power. So how about we do 3x cubed plus x squared plus x. Okay. All right, so let's go back into our guidelines. So this is an odd power. So let's go look at our leading term. And that will tell us what happens far from 0. So 3x cubed plus x squared plus x. So this says if the leading term is positive, which it is, and the power of the leading term is odd, which it is, it's cubed, the polynomial goes to positive infinity when x is positive and a negative infinity when x is negative. Okay, so it looked like this. And once again, close to 0, we don't know exactly what's going to happen. We can tell that when x is when x is positive, far from 0, x is bigger and bigger in this direction, it's going to go to infinity, to positive infinity. When x gets bigger in a negative direction, it's going to negative infinity. So once again, we're going to graph this along with x cubed to show that. Okay, let me shut those two off. And so this is y equals 3x cubed plus x squared plus x. Okay. Now, once again, as we see, that's what happens. So in a positive direction, as we go far away from x or far away from 0, in that positive direction, it goes to positive infinity. Go far away from 0 in the negative direction, it goes toward negative infinity. If I just graph then y equals 3x cubed, yeah, even though close to 0, it's not exactly the same, as you can see. Far from 0, it looks like that. Okay, it does basically the same thing. Okay, let's look at one more example. And so let's do one where our leading term, let's say let's do a fifth order one. So let's say we do f of x is equal to negative x to the fifth plus 4x cubed minus x plus 1. Okay, so negative x to the fifth plus 4x cubed minus x plus 1. Okay, so this time, if we look at our leading term, okay, clearly it's negative. All right, so this is our last case. Leading term is negative, which it is, and power leading term is odd. The exponent is 5, which it is, and basically this is going to be like this flipped. So as x goes to 0 in a negative direction, so the polynomial goes to negative infinity when x is positive. So now you're close to 0. We don't know what's going on. It's going to look like this. When x is positive, it's going to go to negative infinity. When x is negative, far from 0, it's going to go to positive infinity. So it's like that flipped over. Because that's what happens when you have, an even or odd power for your leading term, and then it's negative. Let's take a look at that. The last one. So y equals negative x to the fifth plus 4x cubed minus x plus 1. Okay, yeah, so let's zoom in here and we'll see some kind of interesting behavior close to 0, right? Now, as you can see, we're far from 0, this is what we said happens, okay? So as x gets bigger in the positive direction, it goes to negative infinity. As x gets bigger in the negative direction, it goes to positive infinity. Let's zoom back in. Let's just graph y equals negative x to the fifth along with it. As you can see, close to 0, it's really different. But far from 0, it has basically the same behavior. So what we want to see from that then is that for any polynomial function, this is true of polynomials, not to say other kinds of functions, that basically we can figure out what's happens far from 0 just by its leading term, what its power is, what the exponent is, and then whether it's positive or negative. So let's kind of summarize what we've learned so far. So we learned basically what a polynomial function is. And it's basically kind of a nice function. It's easy to work with. We learned how to find, of course, how to find the zeros of a polynomial function. Same way you find the zeros of any function, set equal to 0 and solve. Okay. You also find out what the multiplicity of zeros is. So if a 0 occurs more than once, based terms on the factor it comes from, then like this example here, negative 2 has multiplicity of 2, positive 4 has multiplicity of 3, and 0 has multiplicity of 1. Okay. And then we learned what the long-term behavior of a polynomial was far from 0 based on its leading term. And from that leading term, we can figure out what it does when it's far from 0. Right? Thank you. Have a good day.